Inside a machine in the Netherlands, a droplet of molten tin is falling through a vacuum. It is smaller than a grain of dust. One laser pulse flattens it into a microscopic disc. A second, far more powerful pulse turns it into superheated plasma. This happens 50,000 times every second. The light travels through roughly 100,000 parts and atomically smooth mirrors, then draws patterns onto silicon with precision measured in fractions of a nanometer. One shipment can require 3 cargo aircraft, 20 trucks, and 40 containers. The newest versions cost hundreds of millions of euros, but money alone cannot buy one. Because ASML cannot obtain a license to sell an EUV system to China. And behind that restriction is a larger story about how technological power is really built. This is an EUV lithography system made by the Dutch company ASML. Lithography prints the patterns from which transistors and their connections are formed. Imagine projecting an impossibly detailed blueprint onto a silicon wafer, then using chemistry to add, remove, and alter materials one layer at a time. For decades, chipmakers used deep ultraviolet or DUV light with a wavelength of 193 nanometers. They made smaller features by splitting one pattern across several exposures. That technique, called multi-patterning, works, but every additional exposure can require more masks, processing, and alignment. Each step adds time, cost, and another chance for a defect. EUV light has a wavelength of just 13.5 nanometers, more than 14 times shorter. At the most difficult layers, a pattern that needs several DUV operations can sometimes be printed with one EUV exposure. A modern processor still requires hundreds of operations, but EUV can reduce complexity at its most difficult layers. That is why it supports the latest high-performance processors and advanced memory. It is not the entire semiconductor industry, but it has become one of its most important gates. The problem is that EUV light is almost impossible to handle. Air absorbs it, so the optical path must operate in a vacuum. Glass absorbs it, so ordinary lenses are useless. Instead, the machine uses mirrors built from more than 100 engineered layers. If one were enlarged to the size of Germany, ASML says its tallest imperfection would be just 1 millimeter high. Then there is the source. The machine releases tin droplets roughly 25 micrometers wide, moving at more than 200 kilometers per hour. One pulse reshapes each droplet, another vaporizes it. Only a small fraction of that energy becomes useful light, so the process must repeat tens of thousands of times per second with extraordinary stability. Meanwhile, the wafer stage checks its position 20,000 times per second, with accuracy around 1/4 of a nanometer. A vibration, contamination particle, or mask defect can destroy the pattern. EUV is therefore not one breakthrough. It is thousands of breakthroughs working together without failure. And that is the first clue to why nobody has simply copied it. ASML did not begin as an obvious monopoly. It was created in 1984 as a joint venture between Philips and ASM International. 47 employees started in a leaky shed near Eindhoven. By 1990, ASMI had withdrawn. Philips was cutting costs, and the venture needed one final lifeline. Philips approved 30 million guilders. Within a year, ASML shipped the PAS5500, the platform that attracted major customers and transformed a cash-draining experiment into a credible competitor. ASML listed independently in 1995, but EUV was a much larger gamble. ASML began the program in 1997. It worked through European research projects, joined an American-led consortium, and delivered early prototypes to research institutes. The first pre-production system did not ship until 2010. Even then, the light source was too weak and reliability too low for mass manufacturing. The machine existed, but the business case did not. In 2012, Intel, Samsung, and TSMC invested directly in ASML's research. The next year, ASML bought American light source specialist Cymer. Production-capable systems followed, but broad factory adoption arrived only around 2020. More than 20 years separated the program's beginning from high-volume use. China must reproduce not only a blueprint, but an era of failed experiments, supplier learning, and factory feedback. ASML calls itself a system architect. That is more revealing than the word manufacturer. The company designs and integrates the scanner, but its power depends on roughly 5,000 suppliers and partners. ZEISS makes the optical system in Germany. TRUMPF supplies the laser architecture. Cymer in California became central to the light source. Other specialists provide vacuum systems, controls, and materials. The customers are part of the network too. TSMC, Intel, and Samsung test new generations and supply years of factory data. That feedback turns experimental performance into dependable production. This creates a monopoly unlike a software platform. It cannot be recreated by copying one product. Much of the knowledge is tacit. How parts behave after months inside a fab, how suppliers correct microscopic variation, and how thousands of tolerances interact. ASML is Dutch, but EUV is not purely Dutch. It combines European industrial policy, German precision engineering, American technology, Asian manufacturing experience, and customers willing to finance a machine that did not yet work. The real strategic asset is not one factory, it is the coordination between all of them. That network also created an unusual political lever. Because ASML is the only commercial EUV supplier, blocking one category of equipment can slow an entire country's access to the leading edge. EUV systems have not been licensed for China. From 2022, the United States expanded controls on advanced computing chips, manufacturing equipment, and related software. The Netherlands introduced authorization rules for specified advanced tools in 2023, then expanded them to additional DUV systems in 2024. The stated concern is military capability. Advanced chips can train artificial intelligence models, process intelligence, and simulate weapons. Washington describes its approach as a high fence around a small yard. Protect the most sensitive technologies without cutting China off from every semiconductor. But that fence is difficult to define. A machine includes technology from several countries. A civilian chip can train a military model. Restrictions in one country fail if another supplier fills the gap. The United States, therefore, needs allies across Europe and Asia. The policy works only if the international network that created the technology also agrees to police it. The West has turned a supply chain into a strategic chokepoint. But a chokepoint is not an impenetrable wall. In August 2023, while the U.S. Commerce Secretary was visiting Beijing, Huawei unveiled the Mate 60 Pro with an advanced processor made by China's SMIC. The timing turned a phone launch into a political message. The lesson was not that controls had failed or EUV no longer mattered. It was that older tools could be pushed beyond their comfortable limits. TSMC's first 7nm class process was produced without EUV. DUV multi-patterning divides a design across masks and rebuilds it through repeated operations. But difficulty rises quickly. Every extra step must align with the previous one. More steps mean longer production, more materials, and more opportunities for variation. If fewer working chips emerge from each wafer, the cost of every successful chip rises. This is the difference between technical possibility and industrial power. A country may demonstrate an advanced processor, yet struggle to manufacture it cheaply and in volume. A teardown proves capability, not yield, cost, or sustainable output. EUV is only one barrier. Leading chips also require design software, other production tools, materials, packaging, and process expertise. Restrictions across several layers reinforce one another. Yet China remains a major buyer of legal equipment and is expanding mature node capacity for cars, industry, and power electronics. Those unglamorous chips can create economic leverage of their own. The contest is not advanced chips or no chips. It is a race across different technologies, costs, and timescales. China's response is not simply to wait for an EUV copy. In 2024, its third national semiconductor fund was registered with 344 billion yuan. Money is flowing toward domestic equipment and materials. Progress is uneven, but failure still accumulates industrial knowledge. China can change the problem as well. Instead of shrinking every transistor, engineers can combine specialized dies in advanced packages. Chiplets connect separately manufactured functions inside one system. Packaging cannot erase the lithography gap, but it can extract more performance from available tools. Manufacturers can improve DUV, replace foreign tools category by category, and reserve advanced chips for strategic uses. Controls make this slower and costlier, but give Beijing a powerful reason to fund it. This is the paradox. A blockade can slow an industry today while making independence a national priority tomorrow. And ASML is not standing still. Its experimental EUV source produced roughly 1 watt in 2010. In 2025, the company reported a 1,000-watt research milestone. High-NA systems use larger, more complex optics to print still smaller features. The target moves forward every year. The question is not whether China can solve individual problems. It is whether it can solve the entire system faster than the existing network reaches its next generation. Export controls do not guarantee permanent Western leadership. They buy time. Time for TSMC, Intel, and Samsung to improve their processes. Time for ASML and its suppliers to develop high-end AEUV. Time for the United States, Europe, and Japan to strengthen manufacturing capacity. But time has value only if it is used. The restrictions carry costs and contradictions. China cannot buy EUV, yet China remains a major buyer of legal equipment and services. China stockpiles tools and funds substitutes, while allies argue over where the small yard ends. The fence can move as technology and governments change. The machine is extraordinarily powerful, but insufficient. It can delay one route to the frontier, not stop experimentation or replace an industrial strategy. The one machine China still cannot buy is real. It turns exploding tin into invisible light, and that light into the most intricate objects humanity manufactures. But the deeper barrier is not sitting on ASML's factory floor. It is 40 years of research, failed prototypes, specialized suppliers, customer feedback, political alliances, and trust between engineers who know that a microscopic defect can stop an entire production line. China can spend hundreds of billions reproducing the parts. What it cannot buy in one transaction is the history that made them work together. Export controls are a bet that this network can keep moving faster than China can recreate it, and the future of the global technology order may depend on whether that bet is right.